This begins EE 544 with Professor Ali Zahid on Thursday, January 16, 2014. We can start with...
I can start? Can I have the overhead, please? Okay, the overhead, please. Scary. Okay, good afternoon, everybody, and welcome to EE 544 again. Let's continue our overview from last time. We started looking at the overview. We went through a simple definition of remove my picture, please. Thank you very much. Okay, we defined what we mean by an RF wireless system. What do you mean by an RF wireless system? It's a collection of subsystems that are operating interdependently. Notice, by the way, not independently, interdependently, which means what? They depend on each other. Those blocks depend on each other. And use, of course, unguided electromagnetic waves. Unguided means what? Not like through a cable or a what? Or fiber or over copper. It's what? Through the air, through using the free space. It's unguided electromagnetic waveform propagation to perform some functions. Some RF wireless systems used to communicate information. For example, in a cellular system, PCS. PCS stands for what? Personal Communication Services System. PCS. PCS in the US operate in the 1.9 gigahertz band. Clear? Don't worry about this. We'll get to it later on. So, cellular PCS systems, the police, the fire department, radio systems, broadcast radio, TV, satellite, all of these are for the purposes of what? Communicating information. But an RF wireless system does not need to be just communicating information. It could also be used to sense some environment. For example, in using wireless sensor, you can sense some temperature, for example, weather monitoring, and so on and so forth. Some of wireless systems add or aid in the navigation, the one that you use for what? Controlling the airplanes or the maritime and so on and so forth, all of these things, including the GPSs and so on and so forth. Clear? So the wireless systems comes in different shapes and forms. We will be studying them. This is a generic RF transceiver. One more time. Transceiver is the abbreviation of what? Transmitter and receiver. This is a very simple diagram. In other words, we are not going to, this is no details in here, but this is just a generic. So we do have the what? The digital baseband, the digital baseband processor. And remember, what did we say about baseband last time? A baseband signal is a signal whose spectrum, what does a spectrum means? A spectrum means what, by the way, in technical terms, the spectrum of a signal is its Fourier transform. Are you familiar with the Fourier transform? That's the spectrum. It tells you what? It tells you the frequency content of the signal. Remember, you can describe a signal in the time domain, or you can describe the signal in the frequency domain. Describing the signal in the time domain through the use of what is known as an oscilloscope. You use an oscilloscope. Whereas if you want to describe the signal in the frequency domain, you use what is known as a what? Spectrum analyzer. Notice, by the way, unfortunately, we don't have a lab for this course. However, throughout the semester, 2 weeks, I will be scheduling extra classes, not on Tuesday and Thursday, on Fridays, to show you how a spectrum analyzer works and how a network analyzer works, but on a piece of paper, unfortunately. Do you understand that or not? Why? Because I need to make sure that when you graduate, if you graduate, it's still debatable, that when you go to work in the industry, you at least know what each device is doing, how it is functioning, and so on and so forth. Clear? Both for the what is known as the spectrum analyzer and the vector or the network vector analyzer. We'll get to that later on. Oh, so the processor here generating digital signal. This is a what? A DAC, converting it from a digital to analog signal. And again, as I told you, for the purpose of what? Smoothing the edges so that the spectrum occupancy becomes what? Becomes more what? more compact, rather than keep getting that sync function. Remember the sync function? Instead of getting this sync function, you try to what? You try to shape. Later on, by the way, we will also refer to this and the filter afterward. We call it what? Pulse shaping. We shape the pulse. For example, GSM using a modulation technique that is called what? GMSK. And the G stands for what? The Gaussian shaped minimum shift keying. Do you know the Gaussian? How does it look like? Sharp edges or smooth edges? Smooth edges, which means what? Its spectrum will become what? More compact rather than what? Rather than these side lobes. Clear? We'll get to this shortly. Okay, then we do have a what? An up converter or a what? Or a modulator. Again, remember what I told you last time? An up converter could be the same as what? As a modulator. But it does not need to be that way. Clear? An up converter or a modulator is what? Is a device that will shift the spectrum from around what? 0, which is the baseband, to around what? To around the so-called carrier frequency, the RF signal. Now, the first question that we need to answer shortly in a minute, why? Why can't we transmit the baseband signal as is? Can we radiate the baseband signal as is without what? Modulation. Now, this one here, we are going to use what? How many inputs does it have, by the way? How many inputs does the modulator have? Has 2 inputs. One is the baseband, the other one is the what? Is the carrier. Clear? From a local oscillator. This is a frequency synthesizer, the oscillator here. So it's a what? The variable, voltage controlled oscillator. Why do we need to modulate? That we need to answer that question in a minute. Just give me a minute. Then we need to amplify the signal, power amplifier. Again, this is all missing a lot of parts. This is just generic block diagram. Remember what I told you last time? A power amplifier needs to be what? Well matched with the what? With the antenna. Otherwise, there will be some power reflected back. And we'll study that when we get to the transmission line. Is there a transmission line here? Yes or no? Connecting the output of the power amplifier to the what? To the antenna. That's a transmission line. We need to understand how the transmission line works also. We'll get to that shortly. This is the antenna. Now, on the other side, this is the receiver. Again, the low noise amplifier. Why did we say that last time? We said that the received signal is going to be what? First of all, very weak. Very weak. And in addition to that, there will be what? A lot of noise associated with it. Remember, by the way, the noise that is coming from outside is thermal noise. And the thermal noise has a what? Has a large, what? A large bandwidth. We need to get rid of as much noise bandwidth as possible. We don't want to introduce a lot of, by the way, there are no devices that will what? That will not add any internal noise. How did they figure this one out? Listen to this. If you design an amplifier, you measure the signal to noise ratio. Did we talk about SNR last time? At least did I bring it? No, I did not. SNR stands for what? Signal to noise ratio. What ratio? Power ratio. Signal power divided by what? Noise power. Now let's assume, forget about dB. Let's make things simple. Let's assume the signal to noise ratio here is 5. If you use an amplifier with gain of 2, what should the signal to noise ratio here be? Why double? Why double? Why? You are amplifying both the noise and the what? The signal. So if the ratio here is 5, the ratio in here should also be what? 5. They found it to be what? Lower than 5. Something must have happened. Did you understand what I just said? They found it to be less than 5. Something must have happened. Why? Because the amplifier is going to amplify the signal, yes, and the noise the same way. See, there must be some noise which was added what? Internally, because of the electronics in the device itself, resulting in what? The signal to noise ratio going what? Going down, degrading a little bit. Clear? We would like the device to add as a small internal noise as possible. Clear? We'll talk about that again in detail. Always remember, whatever you do at the transmitter side, you should be able to what? To reverse it on the receiving side. So instead of having an up converter here, you do have a what? A down converter here, down converter. Now remember, whenever you do have this is the mixer. Whenever you do have a mixer, keep in mind you are going to get what? 2 components at the output of the mixer. You are going to have the sum and you are going to have what? The difference. At the transmitter side, you want to keep the what? The sum. At the receiver side, you need to what? To keep the difference. Clear? Now, in a minute, we'll get to see how we use, why do we use a modulator. This is actually the big picture here. This is a modulator. Is this baseband or RF? Baseband. How do I know that it's a baseband? It is centered around what? 0. Notice, by the way, is this spectrum symmetric around 0? Does it have to be symmetric around 0? We will see later on it does not have to be symmetric around 0. We'll talk about that shortly, but it's premature right now. Tell me about the spectrum at the antenna. Is it centered around 0 or around F sub C? F sub C. And what does F sub C stands for? The carrier frequency. The C stands for what? The carrier frequency. The first thing, one of the first things that an RF engineer needs to worry about is what is this FC? How do you choose this FC? This FC, in other words, you are designing an RF system. You need to figure out what frequency you are going to use, whether this frequency is going to be allocated by a regulatory group or something like that, or is the spectrum what? Is the spectrum unlicensed, unregulated, and so on and so forth. We'll talk about that in a minute. Clear? At the receiver side, what are you getting? By the way, tell me what happened. This is the receiver. Tell me what happened. Compare this one with this one. Is it smaller? Why? Well, the signal got what? Got weaker. How do you know that the signal got weaker? In the frequency domain, you look at the spectrum. Is this the frequency domain or the time domain? Frequency domain. By the way, in the time domain, it's very clear to say that the signal is attenuated because you are looking at the time history of the function. So in the oscilloscope, if you see it lower, then it means what? It means it got attenuated. It's the same idea in the frequency domain. Are you following me or not? Yes? Let's see if you remember one thing. This aside. Let's assume I have x of t as the signal in the time domain. What is in the frequency domain? What is the spectrum? How do I define the spectrum? X of what? F is equal to what? Integral minus infinity. Is this ringing a bell or no bell? X of t e to the minus j 2 pi ft dt. Clear? This is called the spectrum. Question, is it a real function? Or is it in general a complex function? In general, it's a complex function. Why? Because we do have the what? The complex operator in here. Is x of t a real signal? X of t is a real signal. In the real world, we are dealing with real signals here. Clear? So this x of f, I write it as what? X of f is equal to what? Absolute value of x of f times what? E to the j x of f. Clear? What do I call this? This is called the magnitude. No, the magnitude spectrum, not the magnitude phase. The magnitude spectrum. What is the property of this? First of all, can it be negative? High magnitude. What else? What other property? It has to be a what? An even function of what? F. If you get an odd function of f, it means what? You made a boo-boo somewhere. You need to go back and see what mistake you made. Clear? Okay, what do I call this? This. And what is this? How do I get this? I get this by what? The real part square plus the imaginary part square. The whole thing what? Square root. This one is what? Tan inverse. The imaginary over what? Over the real. We call it the phase spectrum. And what is it? Even or odd? This is an odd function of f. Why is it an odd function of f? It's a tan inverse. Tan inverse is an odd function of f. Clear? Clear? Okay, good. So this is just the basic idea that we are going to be. In a minute, we need to answer the following. What happened? This keep moving and it make me dizzy. Up a little bit. Sorry. Yes. Clear? Okay, good. Now, the environment. Where are we going to send these signals? We are going to send it over what? Over a wireless channel. That wireless channel, is it benign or is it severe? Benign is what? Does not an example of a benign channel is a satellite channel. Why? Because a satellite, you are going to point your transmitter to what? To a satellite orbiting in a geosynchronous orbit. Clear? So the effect of what? The environment, for example, buildings, lampposts, the cars and stuff like that will be what? Negligible, because your antenna is pointing toward what? Toward the satellite. But in a cellular environment, that's not the case. In a cellular environment, everything will be what? Terrestrial. And all of these problems with the wireless channel becomes what? Becomes extremely severe that we need to worry about. Now, let's understand what it is, first of all. When you are what? When you are propagating every electromagnetic thing, anything that is unguided, you are not going to be what? You are not going to be able to control the path the signal will go through. I want you to see this before I continue with this. I want you to see this. This is a base station. This is your car. Junk car here. Okay, old car. Yes? What do I have? Tell me. Is this a path? This one. That I call it LOS. LOS stands for what? Line of sight. Do we have to always have a line of sight to be able to communicate? Why? Because RF signals penetrate what? Penetrate walls. It can be reflected from the ground. It can be diffracted from the buildings. See this one you're building? There are some signals that will be what? Creep around the what? Building, sharp edges of the building. We have what is known as what? Diffraction. Could we have scattering? Look at the scattering. The lamppost, the signal will come into the, by the way, what is the difference between scattering and diffraction or reflection? In scattering, the object is very small compared to what? Compared to the wavelength. Are you following or not? Whereas this one is what? It's larger than the wavelength. Did you understand that or not? In scattering, for example, even the raindrops, when it rains, if the RF signal hits the raindrop, it will what? Scatters all over the place. Is that good or bad? That's bad because you are going to lose some what? To lose some power that was destined to go to that receiver, to that particular receiver. So we have, for example, excuse me, we do have a what? We do have a reflection signal. We do have what? A line of sight signal. By the way, if this one happens to go where? Look at this mobile. If it happens to go in here, then what is this behaving at? This one behaving like a what? A shadow. In other words, you are going to experience what? Shadowing. Clear? Now, you might say, so what is the problem? What's the problem is that you are creating multiple paths, but with different what? Different delays. Different delay. Why? Because do you remember how do you measure the propagation delay? How do you, if I tell you, are you familiar with the propagation delay? No, no. Those of you who took networking should know what the propagation delay is. Propagation delay. Still waiting. Where is the speed of light? In the numerator or in the denominator? You give me the denominator before the numerator? You give me the numerator first. Is the what? Is the distance? Distance traveled in what? In say meter. Divide by what? Speed of light in what? Meter per second. Always remember, whenever you write an equation, make sure the units make sense. So if you put meter in the top, in the bottom, you cannot put weight in kilogram. You are going to get what? You are not going to get second here. So it's meter divided by meters per second. Those are different what? Different delays. Now, you might say, so what if different delays? What will happen? Jump with me a little bit to page. I'm sorry. Jump with me to a little bit page to 46. I'm sorry about that. I want you to see this so that you understand what I'm talking about. This is what is known as what? Multipath propagation. Multipath. Tell me here, how many paths do I have? This one, and stop sign, and so on and so forth. Now, answer me this. What does this mean? Look at this mean. This is the pulses that you are sending. How many pulses that you are sending? This is a base station. How many pulses is he sending? He is sending 2 pulses. Look at this. This one was received what? Here, 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 maybe here. This one is received here, here, here. Are they going to interfere with each other? They are going to interfere with each other. This is the same transmission, by the way. It is the same transmission. You understand what I'm saying? In other words, it's coming from the same what? From the same base station. One symbol will interfere with what? With another symbol because of the difference in the delay. Clear? Generating what is known as ISI. I don't want you to forget ISI. ISI stands for what? Intersymbol interference. Intersymbol interference. Why do I call it intersymbol? This is between your symbol. This is not interference from another user. Do not confuse that. Interference can be what? Within yourself, you are interfering with yourself, or interference coming from outside. By the way, even the interference coming from outside could be intentional interference. Somebody is intentionally jamming your transmission. You follow me or not? Or unintentional. You make a phone call, I make a phone call. I'm not intentionally what? Interfering with you. We just happen to be using frequencies that are close to each other. Clear? Okay, good. So now what happened? All of these pulses are going to be received at the receiver. Some of them are going to be received out of phase. What do you get by adding a sign with a minus sign? First of all, what does minus sign mean? Means that you have experienced what phase delay? Phase shift, I said phase delay, I'm sorry. Phase shift, how much? 180. if you add a sign with a minus sign, what happens? You get 0, which means what? All the information that was superimposed on the carrier signal got lost. Did you understand that or not? I want you to see what will happen. Tell me what will happen. This is the power. This is the signal power at the receiver. This is the signal power at the receiver. Notice, by the way, at the transmitter, I transmitted at what? At fixed power. Ideally, if there are no attenuation, if there are no losses, by the way, even if there is no multipass, will your signal degrade? That's the propagation losses. The propagation losses, as I will show you in just a second. Clear? Tell me what happened to the signal. At some, you see this one here? It faded. The signal faded, which means what? It lost a lot of what? A lot of its power because of what? Cancellations between the multiple versions that you are receiving through multiple delay. Are you following me on that? Now you might say, okay, so what happened here? You have to remember that the channel is a time varying channel. It's going to change very quickly. Are you following me on that? The variation. Sometimes it's what? You have, listen to me. What are we talking about? We have not talked about that yet. But when we talk about RF signal, give me some arbitrary RF frequency. 1 gigahertz. Just an example. 1 gigahertz. Yes? Okay. What is the wavelength? If it is 1 gigahertz, what is the wavelength? Wavelength means what? 10 centimeter. Yes? What does that mean? It means that if there is a relative motion between the transmitter and the receiver, that corresponds to what? 10 centimeter. Is that 10 centimeter long or short? It's just 10 centimeter. The whole thing will what? Will change. Did you get my point or not? Clear? These types of channel, we call it what? Time varying channels. It's going to change. It's not time invariant. Clear? Clear? Okay. What am I talking about when I say time invariant? We are talking about the impulse response, which is what? Which is h of t, impulse response. Did you forget, is this ringing a bell or no bell? No bell. What is h of f is called? Still waiting. What do I call it? No, I want system. No, I don't want you to call it transfer function. I want to call it what? The frequency response. The word the transfer function is usually reserved to h of s, which is the Laplace transfer. I don't want you to use transfer function. Frequency response of the system. Clear? Of system. Which is what, by the way? Which is the Fourier transform of what? Of the impulse response. Clear? Okay, minus infinity to infinity. But when I talk about time varying channel, what am I saying? I'm saying that the impulse response is going to change with what? It's going to change with time, especially if there is, again, especially if there is a motion in there. So, additional, again, every time what? There will be quick changes in the power received. What does that mean as far as the receiver design is concerned? One of the most important parameters in RF design is what is known as the dynamic range of a receiver. What is a dynamic range of a receiver? We are going to designate it later on. Don't worry about it. Right now, just listen to me. Dynamic range of the receiver will be designated by dr. And it is measured in dB, which means what? It's not a power. It's a ratio. Did you understand that or not? dB stands for what? Decimals. The dynamic range of a receiver is the difference between what? The highest signal power that the receiver can what? Can process. Are you following? Without what? Without getting blocked. Getting blocked means what? Getting saturated. Minus what? The lowest power that it can sense. Are you following me or not? This lowest power, by the way, we will refer to it later on as the receiver sensitivity. The receiver sensitivity. The receiver sensitivity is governed by the noise level, whereas the maximum power is governed by what? The nonlinearity in the system. Do you understand what I'm now? I don't want to increase the... How does an amplifier characteristic look like? This is a premature question. Premature question. This is the input power. This is the output power. This is a premature question, but I just want to make sure you understand. Is it linear? It's like this. And then what happened? And then what happened? Actually, it goes down. Are you following me or not? Which means what? As the input power increases, you are actually getting what? You are getting actually what? Compression. Did you understand what I just said or not? I don't want to operate in what? In the compression mode. Clear? But I also don't want to operate in here, because in here the efficiency of the amplifier becomes what? Lower. I want to operate the amplifier at what? Closest to the maximum efficiency. So I would like to operate it what? Here, somewhere in here. Now keep in mind, once you get what? Non-linearity, all the what? All the side spectrum, all the side lobes that you get rid of using filtering will what? Will come again, will regrow again. Do you understand? If you do have what? If you do have non-linearity. Clear? I want to show you simple, very simple, silly example, just to show you the point. Let's assume I have a square law device. Question, is this a linear or non-linear system? Non-linear system. Apply cosine 2 pi f naught t or fct, doesn't matter. Yes? How many frequency components do we have here? What do I have? I have cosine square, which is equal to what? 1/2 plus 1/2 cosine 4 pi fct. Did we create the second harmonic? Is that second harmonic, could it interfere with other devices, with other transmitters operating at that other frequency? That's what I meant by generating what? Generating all of these side lobes and stuff. You might say, Professor, but this is just the second harmonic. It's not a side lobe. But you have to remember, the input to the square law device is not a pure carrier. This is a pure carrier. In reality, the input to the amplifier, to the nonlinear device, is a what? Is a carrier modulated by who? Modulated by the information. Yes or no? Are you following me, or you are losing me? You are not going to get you are not transmitting only one carrier signal with no information. Clear? This is just to show you, how do you know that the system is linear or nonlinear? A nonlinear system create frequency components that were not available at what? At the input. Is there a DC component at the output? Was there a DC component at the input? No. It created a new frequency component. Was the second harmonic present in the input? It created it at the output. Clear? A linear system may what? May amplify some frequencies, may what? Reject some frequencies, may attenuate some frequencies, but it does not what? Create new frequency components that were not available at the input. Clear? Okay, good. Now, so all of these together, by the way, look at this. At this point in time, what is the received power? 0. Now notice, by the way, all of the information that was superimposed on the carrier at this time are what? Lost. You follow me or not? The multipath is a major issue. I want to show you one. I want to show you this time. This one should be before this one. I'm sorry. This one. I want you to see this. Tell me what happened here. This is attenuation and propagation. When you transmit it at what power? This is the power. This is the sensitivity. Look at the noise. This is the noise. Sensitivity is just what? Just at the noise level. As you propagate, even if there is no what? Even if there is no multipath, is the signal what? Is the signal attenuated? Signal cannot be attenuated below what? Below this one. This is called what? The minimum signal to noise ratio. You are not going to be able to what? To sense the signal. You are not going to be sensing the signal. You are only going to see what noise. The signal is there, but it is what? Way below the what? The noise level. You are not going to see. You think that this is a what? Just some noise, background noise and something like that. Clear? Now, we'll talk about that later on in detail. Let me ask you a question. What do you think?
Is it acceptable if the noise exceeds the sensitivity of the receiver?
It's shown in here, but actually the sensitivity of the receiver should be a little bit more than 2 or 3 dB above the noise level. Are you following me or not? Above the noise level. Now, you do understand what do I mean by this signal to noise ratio here? This signal to noise ratio means what? The signal power. By the way, in here, the signal power exceeded it. You follow me or not? Okay. But it cannot go below what? This line. Because this line is what is referred to the signal. Notice, by the way, in here, I'm only showing you what? The effect of the propagation and the effect of the multipath. In addition to all of these, is there possibility of interference? We'll talk about the interference in just a second. Now, some ways of overcoming the effect of multipath. You will study it in 535. 535 is the mobile communications class. It is what is known as what? Diversity. You will have different diversity techniques. For example, you would have frequency diversity. Frequency diversity means what? You transmit your signal or using what? Multiple frequencies rather than what? Rather than a single frequency. So that if one frequency experience fading, the others will what? Will be okay. It could be time diversity. Time diversity means what? You transmit your signal multiple times at different times. Clear? Now you might say, but what difference does it make if you transmit them multiple times? Remember what I told you a moment ago. The channel is time varying. Maybe during that time it's not good, during the other time it's good. You could also have a spatial diversity by including what? Multiple antennas separated by a certain amount of wavelengths, such that you are going to what? You are going to make the received signal in a constructive way rather than in a destructive one. You will learn this one in 535. Clear? We don't get into diversity in this class. We don't have time. I just brought it up into your attention so that if you take the class, it will help you. Now, I want you to see one thing here. I did not talk about interference in here. Could there be interference? Why? Because the channel is what? The channel is being shared. Are you following or not? Now, when you talk about interference, we have what is known as what? Now, we are not going to talk in this class about what's jamming. Are you following? We are peaceful people. Just a joke, just a joke. So, but you do understand what jamming means. The first thing in a warfare environment is what? Most important is what? Is the jamming. You try to jam the radio communications between your enemy commander or the field soldiers or whatever the case might be. But we are not going to be interested in this course. What we are going to be interested in here is two types of interference. This is what is known as what? ACI. What is ACI stands for? Adjacent channel. Interference. What adjacent channel? Now, remember what I told you last time. We are talking about an adjacent channel within the what? Within the desired band. Within the, you notice I did not say within the desired channel. I said what? Within the desired band, there are what? Adjacent channels that might what? That might interfere with you. Now you do understand that one of the most important part of designing an RF transmitter is to make sure that your emission, your spectral emission, who's you as a transmitter, needs to be confined within what? Within the channel that was allocated to you. You don't want to spill into what? Into other channels, because you are going to cause interference into them. Did you understand what I just said? That's one purpose of the transmitter. Important thing. You need to make sure that your emission, your transmission emission or your spectral emission is confined within the channel that was allocated to you. What is the second important part of the transmitter? You need to have the right what? The right amount of power to reach what? To provide for coverage. Are you going to provide for coverage? Otherwise your signal will die down. Nobody will receive. Clear? Okay. And of course you need to what? You need to minimize the cost. You need to minimize the power consumption. All of these issues. Okay. Now, again, what is the other one? CCI. CCI stands for what? Co-channel interference. Let me jump here a little bit to show you what I mean by that. Co-channel interference. If I can't find it. I messed up my chart. Here. This is a what? This is a cellular architecture. Now, what do you notice about this cell and this cell? This cell and this cell, they are going to use the same set of what? The same set of frequencies. Yes or no? Is this a transmitter going to be what? Interfering with this transmitter? Yes, it is. Now, you might say, but there is a spatial separation, which is fine. The spatial separation is needed. Are you following or not? Is needed. Now, we will see in just a second that the propagation, the losses, the signal, how much power it's going to be losing is proportional to the what? To the square of the what? Of the distance. Are you following me or not? Cannot hear you. That, which means what? It means if it's did I say proportional? Inversely proportional. I'm sorry, inversely proportional to the square of what? Of the distance. What distance? What distance? The distance between the transmitter and the what? And the receiver. Even that inversely proportional to the square of the distance, this is assuming we are operating in an open environment, like in a rural environment. Rural means what? There are no tall buildings, not too many obstacles and stuff like that. But if you are working in a dense environment like, for example, in downtown LA and stuff like that, the signal power will degrade inversely proportional to probably the distance to the power what? 4. Or even more than 4 in a dense environment or even in a suburban environment. Did you get this or not? The question here about that is that there is no empirical formula, or there is no formula that I kind of plug. It's all based on what? Measurement. And companies like Qualcomm or something, they take their what? They take their truck and they measure what? They measure the power, so the received signal strength power, RSSI. They call it RSSI. They measure it in what? In multiple locations within the area, and they come up with what? With a model, mathematical model to cover how much is the signal is losing. Clear? Oh. So if they are separated, the longer the distance is, it means what? The signal will lose its what? Its strength, which means the interference will become what? Will become lower. Clear? In using CDMA, what does CDMA stands for? Code division multiple access. Users are allowed to use what? The same frequency, are allowed to use the same what? At the same time, but using different what? Codes. Are you following me on that? Now, in this case, the codes are supposed to be what? Orthogonal. Orthogonal means what? The dot product between them is equal to what? 0. So the receiver is able to distinguish between them. However, they are orthogonal when they leave the what? The transmitters. When they reach the receiver, they are no longer what? They are no longer orthogonal. They are going to lose their orthogonality. And if they lose their orthogonality, is that going to be a co-channel interference? That is going to be a co-channel interference because you are transmitting using the same what? Using the same frequency. Clear? Always keep in mind, by the way, even the frequency can change if there is a relative motion between what? Between the transmitter and the receiver. Clear? What do we call this? That's the Doppler effect. That's the Doppler effect. That will even make the what? Make the channel even worse. Are you following on it? The idea of how to calculate all of these is what is known as a what? As a delay spread. A delay spread means what? What is the maximum delay encountered by a signal? Same signal. Remember, you are going to receive multiple versions. Clear? What is the maximum delay? Minus what? Minus what is the minimum delay? Clear? This is called what? The delay spread. Clear? No response. Clear? Question. Is that deterministic or is it a random variable? That's a random variable, which means what? You need to describe it using PDF. You need to talk about what? Talk about the standard deviations, variances, and so on and so forth, mean or whatever, all of these things. Clear so far? Okay, good. Now, this is what I meant by the co-channel interferences. Clear? Okay, good. So again, the noise interference level, hard to predict. They are time varying objects all over the place. The signal is going to be what? Varying based on the environment from one value to another value, and so on and so forth. Okay, I lost the track. Where is picture? Okay, this is the one that I just showed you about, all of these, reflection and diffraction and the scattering. Clear? Scattering, again, as I told you, this is like the lamp post or the raindrop and so on and so forth, all of these things. And diffraction from the hilltops and so on and so forth. Okay. Now, why is it so complicated? Why is RF so complicated? I think I showed you this last time. It is very complicated because you require the knowledge of what? You would require the knowledge of what? Of many aspects of what? Of the field. You need to know a little bit about antennas. You need to know about propagation, channel modeling. Again, as I told you, these are separate courses. Channel modeling, in this course, we will not talk about channel modeling at all. This is what? This is EE. How many of you are taking 535? Okay, good. So this will augment the description. Microwave circuit design. This is our interest is in the transceiver design. Signal processing, embedded software, packaging, switching, and so on. So reliability. And last but not least is systems engineering, of course. Clear? RF, again, as I told you last time, is one of the most complicated, one of the most complicated issues or fields in engineering. Let's skip here for just a second and go a little bit more into technical. We'll continue with this. I told you last time, the concept of what? Of a frequency. Let me show you the spectrum first. Are you following me or you are losing me? No response. What happened to the spectrum? What do you notice? This is a spectrum allocated by what? FCC. Yes? Is it crowded or not crowded? Very crowded. Are you following or not? Very crowded. By the way, that's one of the reasons of the development of what is known as cognitive radio. And cognitive radios, the radios are smart enough to what? To try to sense whether there are any holes or whether are the what? The non-cognitive radios are not using the spectrum, and you can what? Sneak by and use the spectrum, and so on and so forth. Clear? It's getting so crowded. Now, I will be emailing you the URL of a couple of companies that distribute posters for these, big posters, very nice. And if you order them, and if you get it for free, I will give you extra credit. But if you don't, I don't get you extra credit. If you tell me I can download it from the web, I tell you I already did. This is how it looks. Can you read it? Can you read it? If you can read it, it means what? You are a Superman or a Superwoman. Okay. The spectrum, again, as I told you, could be a licensed band. Licensed band means what? Means the operator needs to pay money to the FCC to allow them to operate, and they charge. They charge. In the unlicensed band, unlicensed means what? Means you can operate without what? Without any license, as long as you adhere to the what? Regulations from the FCC, that you do not cause interference, unacceptable interference to your fellow users or to the what? Or to the users in the nearby licensed band. Operating in the unlicensed band is the what? Is the 802.11, the Wi-Fi, clear? The UWB, anybody? The ultra-wide band, which is, by the way, those bands are operating much higher in the frequency range, roughly 50 or 60 gigahertz. At that time, at that range, there are not too what? Not too much what? Not too much, what is the word? Not too much crowded. It's not too much crowded. Why? Can you tell me why? Why operating at extremely high frequencies? Let me show you the frequencies first. RF, when you talk about RF, this is from our textbook, but I cannot make the chart. Okay, so you have, for example, super low frequency, ultra low frequency, very low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, extremely high frequency, tremendously high frequency, all types of what? All types of terminologies that are used. Yes? Answer me the following question. Why operating at very high frequencies like in this 50 gigahertz or 60 gigahertz? RF, by the way, usually it's up to 100 gigahertz. Everything outside of 100 gigahertz, you become in getting what? Getting into the optical stuff or very close to the optical stuff. Clear? Below the lower range is like, let's say, 10 kilohertz. Below 10 kilohertz, it becomes what? It becomes baseband. Let's put it this way. It does not become RF. Clear? Okay. Why operating at very high frequencies is not desirable? The signal, by the way, loses its strength. The signal loses its strength faster at higher what? At higher frequencies. So the operator, they are in the business of making what? Making money. They want to generate revenues. If they are going to what? If the coverage is going to be limited, then what will happen? What will happen is that you are going to reduce the revenue, review the coverage. Always remember the rule of thumb. When you design an RF system, at the beginning, you design an RF system for coverage. For coverage, which means what? You want to cover as much as possible. After you design it for coverage, then you try to improve it to increase what? Capacity. The coverage becomes what? Becomes more, more important at the beginning. At the beginning, becomes more important than the capacity. When you want to increase the capacity, we will see that later on, and you will study it in 535. I hope he discussed cellular architecture. Did he mention cellular architecture? I hope you will see that he will divide the cell into what? Into several sectors using what? Sectorized antenna, directional antenna, so that you can reuse the frequency sooner rather than what? Later. Actually, sooner rather than later represent time. What I meant to say is what? Closer rather than what? Farther away. The antennas becomes like this. This is the directional antenna here. Becomes I divide it into how many sectors in here, for example, 1, 2, 3, 4, 5, 6. The antennas will become what? Will become direction. Notice, by the way, the antenna will also have somewhat side lobes and back lobes, but their effect will be what? Negligible, because these are the side lobes, and especially the back lobes will be negligible. Clear? You can reuse the frequencies to increase the capacity. But when you design your system at the beginning, you need to design it based on what? Based on coverage. You need to attract people first. You need to let them know that you can what? You can reach them, rather than what? How much capacity or and if you see the evolution of the wireless systems, which I will show you in just a second, you will see at the beginning, it was, for example, second generation, anybody? Data, anybody. Second generation for data, not telephony. It was 10 kilobits per second. Is that high or low? 10 kilobits per second is nothing. But that was the second generation. People were just trying to get any rate for data. Second generation was just for phones. Third generation right now, it increased to what? Increased to roughly what? Roughly 1 megabits per second or twice. And the fourth generation, the LTE, for example, is promising, or the WiMAX, for example, is promising all the way, maybe reaching what? Reaching 100 megabits per second, but for a shorter what? A shorter range. For example, the IEEE 802.11ac or something like that. Clear? Okay, keep that in mind. Okay, so the spectrum could be what? Could be reused. This is the square spectrum again. This is the electromagnetic. You can see some services, the AM radio here, FM radio here, terrestrial here. They are trying, for example, analog TV. FCC decided what? I don't want analog TV anymore. They want to digitize the TV signal. Digitize TV signals to allow for what? Compression of a TV signal, which means you can support more TV channels within the same what? Within the same band. So they took away some of the what? Analog TV channels, and they are trying to allocate this band to some new what? Broadband applications. Are you following or not? Some new broadband applications to provide for what? To provide for more attractive applications rather than just what? TV or whatever the case might be. Yeah.
Communication system that operates at a very high frequency, more complex and expensive.
That is absolutely true. The question is what? If you open, by the way, I always forget, I need to repeat your question because then students cannot hear you. They can only hear me. So don't get irritated when I repeat your question. It's for their own. The higher the frequency, the complexity, the power requirement of your equipment will always what? Will always increase. I don't know if you have seen how many, you are too young to remember. Have you seen the telephones that was used to communicate to a satellite? Satellite telephones. No, you haven't seen in the movies or something? You know, bulky, you need to carry it. In other words, you can use it as an exercise. And this is how bulky it is. Why? Because it needs, first of all, it's transmitting at what? At gigahertz range for the satellite, depending on whether it's the KU band or the KA band or whatever. But in addition to that, the signal has to go through what? Has to go through roughly 35,000 kilometers to reach the geosynchronous satellite, which means what? You need to pump enough power to what? To reach the satellite. Did you get this or not? So again, rule of thumb, as you increase the frequency, the cost will go what? Providers, the service, I'm a service provider. I don't want to spend too much money on it. I just want to make money. You follow me? So I prefer like the cellular. You look at the cellular operating at what? 800 megahertz or the what? 1.9 gigahertz. Something reasonable. Are you following that to allow you to use what? Those small gadgets, small, you can put it in your pocket and stuff like that. So we will talk about that. But however, keep in mind that in our cost, the cost will not be an issue. Somebody else will pay for it. Not from our pocket. We are going to be heavily only what? Trading technical issues, not cost. Do you understand that or not? So the cost is a minor thing that we need to understand here. Okay. Now, let me show you before. Let me show you. I'm jumping all over the place. I don't care, but I want you to understand the overall picture before we get to some applications. Modulation. Modulation. Why do we modulate? So let's getting back to the what? Getting back to our block diagram. Answer me the following question. Can we transmit this? Can we transmit the baseband signal after changing it to what? Analog signal through the bulk shaping? Can I transmit it to the antenna right away? By the way, I can amplify it. Okay, amplifier, I can amplify it. Can I transmit it? Can I radiate this signal right away without modulation? The answer to that is what? Is no, I cannot. Why? We need to understand that. But before we get to that, I need you to understand the concept of modulation. A modulator has how many inputs? One more time. Has 2 inputs. And most of the time, by the way, you only see one input.
The time is 12
because the
o'clock.
other input is what? Internal. So, for example, if you connect your PC at home to a what? To a DSL modem or a cable modem, you are only going to see the what? The baseband port of the modem. The internal, the other one, the local oscillator is internal. You don't see it. Okay, so the modem has what? Has 2 inputs. This is the modem. And the first one is called the what? The carrier signal. What is the mathematical model of a carrier signal? Mathematical model for a carrier signal is what? C of t, C stands for the carrier, is A cosine 2 pi F C T plus what? Theta or phi. This is the what? This is the modulating, look how am I going to call it? The modulating ing, the modulating signal. Another name for the modulating signal is the what? Is the baseband signal or the information signal. Clear? Call it what? M of t, for example. M of t. What is the spectrum of this? If this is M of t, what is the spectrum? M of f. Clear? Question. Let's see if you remember from 301. What is the spectrum of this guy? Single what? A delta function. Delta function. In other words, you would have a what? You would have a delta function at what? At f sub c and what? Minus f sub c. Notice, by the way, frequencies are only positive frequencies. This is the minus. It's just because of what? Just because the Fourier transform is a complex transform, so it depends on what? Depends on whether it's a plus j or what? Minus j. Okay, keep that in mind. Now, answer me the following question quickly. What is A? Constant or not constant? Constant. The peak amplitude is constant. Question. What is f sub c? Frequency. Constant or not constant? Constant. What is theta? Is the phase. Phase, by the way, is a relative measure. In other words, I have some reference and I'm comparing the phase of my signal with a reference. Did you get it? Question. Constant or not constant? Constant. Everything is constant. Generated by what? By the local oscillator. By the way, I'm assuming they are constant theoretically speaking. Even if you don't do modulation, there will always be some drifting. The local oscillator, they will what? The frequencies will get a little bit what? Drifted and so on. So it's accuracy, just like any clock. We talk about later on, we will talk about what? The accuracy of the clocks or the accuracy of the synthesizers, if you would like. What is modulation? Let's understand what modulation before we write in here. What is modulation? Modulation is the process of varying one or more parameter of a carrier signal. How many parameters? One more time. 3 parameters, the amplitude, the frequency, and the phase. All of them are what? Constant. Modulation is the process of varying one or more parameters of a carrier signal in accordance to the what? To the information or the baseband signal. If I change the amplitude, then I have what is known as what? Amplitude modulation. If I change the frequency, then I have a what? Frequency modulation. If I change the phase, then I have a what? Phase modulation. Now, question, before I continue. Let me first of all write what is this. This is called anybody? This is called the modulated ED, the modulated signal. And let's call this one X of t. X of t. The modulated signal. Clear? What is this signal? Analog or digital? Analog. Okay. Now, the information, could it be analog? What do I call this? I call it analog modulation. Could the information be digital? What do I call this? Digital modulation. But you need to understand one thing. The signal itself, the modulated carrier, is a what? Is an analog signal carrying digital information. Or it is a what? An analog signal carrying analog information. So when you hear people talking about what? Digital modulation, I don't want you to say what? The carrier is what? Digital. The carrier is always what? An analog signal, but the information that it's carrying is a what? Digital information. Now, most of the time currently or in this course, we are going to assume that the signal is what? Digital. If the source happens to be what? Analog, then it means I'm going to apply it to a what? to an ADC. ADC stands for what? Analog to digital conversion. Before what? Before I modulate. Before I modulate. Clear? Okay, good. Now, so if you look at, tell me what is this? This is the carrier's, what is this? No, sorry, this is the message signal. By the way, what do I call this message signal? The message signal, the modulating, the baseband. But what is it? In this example, it's a single tone. You follow me on that? It's a single frequency. That frequency, by the way, has to be below what? Has to be below 20K to be what? To be an audible signal. Otherwise, it's not audible. Are you following? How are you transmitting message signal which is not audible? Clear? This is just a sine wave in here, or a sinus or single tone to show you the diagram. In reality, is it like this? It's not like this. You are transmitting information. But the spectrum of the information that you are generating is centered around what? It's centered around zero. That's why we call it a baseband. Tell me, what did I change here? No, sorry, what is this? That's a carrier signal. Is it constant amplitude? Constant amplitude. The frequency constant? Compared to this one, is it much higher or lower? Much higher. We will see why in just a second. So the ratio between the frequency by the way, what do I call the maximum frequency component in the modulating signal? The modulating signal, remember, it is centered around what? Zero. Yes? Start from zero. So the maximum frequency, this is what we refer to as what? The bandwidth of the baseband signal. The bandwidth, not of the RF signal. The bandwidth of the what? Baseband signal. Did you get it on that? Yes or no? Okay. Which one has a higher frequency? This one much higher frequency than this one. Can you hear this? No, you cannot hear this. If you hear this, again, as I told you last time, you don't need a radio. Just do like this and smile. Smile means what? You are receiving something. You are not receiving anything. You are just making believe. Okay, tell me, what did I change here? I changed the amplitude. Are you following me on that? I changed the amplitude. You can see right away, this is a type of modulation which is called what? Non-constant envelope. Is the envelope constant or non-constant? Non-constant. I want you to see the envelope. Does it follow the modulating signal? We cover modulating signal, and we will see that we can decode, not decode, we can detect the demodulator for this Y is a very simple what? Envelope demodulator. Later on. But did you get the idea? I want you now to tell me, what did I do here? What did I do here? This is again the message signal. This is what? Is it analog? Is the information analog? Can you tell me, what did I change here? Actually, I cannot tell. It could be what? It could be an FM signal, or it could be a what? A PM signal. What is the point that I'm trying to make? The point that I'm trying to make is what? Is that if the information is an analog information, you will not be able to tell whether it's a what? FM or whether it's a what? PM. By just looking at it. Analytically, if you do it analytically, you will be able to tell. But by just looking at it, you can. But you can see that the amplitude is not changing. True or false? True. What do I call this type of modulation technique? Constant envelope. Question. In reality, when you are transmitting an FM signal, will the amplitude be received constant, or will there be some fluctuations? There will be some fluctuations because of what I told you about a moment ago, the attenuation, the fading, and stuff, all of these things. Clear? So in an FM receiver, as we will see later on, we will see that one of the block diagrams in an FM receiver, or one of the circuits that we need to design, is a limiter to try to what? To try to get back the amplitude to be what? Constant. Are you following me or not? However, a limiter is a what? Is a nonlinear device, which means that it will generate what? It will generate some harmonics and so on and so forth. Clear? Clear? Oh, by the way, later on we will see the harmonics is not really the big issue. The big issue in the design of RF is what is known as the intermodulation components. The reason for that, because harmonics usually are located out of band. Do you agree or you do not agree? If the band, for example, if your carrier is F sub C, what is the second harmonic? 2F sub C. Chances are 2F sub C is what? Out of band, which means what? Any filter can get rid of it. Clear? But intermodulation components, especially the third order intermodulation components, we don't know what that means yet. We'll get to it shortly. Might result in components within the what? Within the band. It might even be within the what? The desired channel. You might say, okay, so I filter it. You filter it, you are filtering the what? The channel itself. Did you get my point or not? Okay, good. And we will talk about that later on. Did you understand this? Tell me, what do I have here? What did I do here? The modulation now is what? The information is what? Digital. That's what we are interested in. If digital, we are going to be talking about what? R sub what? B. R sub B stands for what? The bit rate. Clear? And what am I going to talk in here? I'm going to talk about R sub S, which is the what? Signaling rate. How do I measure the bit rate? Bits per second. How do I measure the signaling rate? It's baud. Actually, people call it baud per second, but I just want you to call it baud. Baud is already a rate. But if you wrote baud per second, it's okay. I mean, I'm not going to be that picky. I am picky, but I mean, you know, this is too much picky. So when you talk, I mean, people in the industry, you just say baud, they will understand that. Clear? Or if you just want to say signaling rate in what? In samples per second or signals per second and so on and so forth. Tell me now, first of all, what is the relationship between RS and RB? Anybody? RS is equal to what? RB over what? K. Where K is the what? Is the number of bits per what? Per symbol. The number of bits per symbol. Tell me now, if K is equal to what? Now, if we are dealing with binary modems, you are blocking the clock. Can you move your head a little bit? Yes. Yeah, you are too tall. Okay, binary. What did I want to say? Thank you, sir. You are very nice. You are very kind, I mean. A binary modem. What is a binary modem means? Listen to me. Binary modem. Every bit goes in, a signal goes what? Out. A bit goes in, a signal goes out. What is the bit rate in this case? Is it equal to the signaling rate? It's equal to the signaling rate. The bit rate is equal to the signaling rate. Clear? I need to make sure you understand what a bit rate means. Too many things to cover. Answer me this question. Let's assume this is what? 1, 0, 0, 1, 0. And let's assume this is 1 second. Just an example. Just an example. What is the bit rate here? RB equal to what? 5 bits per what? Second. What do I call from here to here? This is called T sub B, and T sub B is equal to what? Bit duration. And what is the relationship between RB and TB? RB equal to what? 1 over what? TB. Are you following me on that? Yes? Now, I want you to understand one thing here. If you make TB what? If you make TB narrower and narrower, what does that imply? You are transmitting what? Faster. What does it matter? Or sorry, what does it imply if you, I want you to look at this pulse. And I want you to look at this pulse. Both of them are in which domain? In the time domain. Can you tell me in the frequency domain what will be the difference between them? This one will be like this. Are you following me or not? What will this one be? Follow me. Are they both sync? They are both sync, but this one has what? Has expanded, which means what? This one has higher frequency components rather than this one. This is the main lobe. This is which, what is this? This is F. What is this? This is 1 over what? T sub B, or it's RB. Clear? Approximately. Clear? Which means what? As you make TB smaller, the bandwidth will get what? Will get stretched out. Did you get my point or not? Okay, good. Now, let's get back to here. Tell me in here, what is the bit rate? Fine. What is the baud rate? I just told you don't say baud rate, but that's fine. What is the baud rate is what? Fine. What kind of a modem is this? Binary modem. Tells me what type is it? Is it amplitude modulation? Yeah. But if it is digital, they call it what? ASK. ASK stands for what? Amplitude shift keying. Amplitude shift keying. Question. How many different amplitudes do we have? 2 different amplitudes. One representing the what? 0, the other one representing the 1. Question. Which one has the higher amplitude? The one representing the 1 or the one representing a 0? representing a 1. Could it be the other way around? Of course, as long as the receiver knows about it. You cannot tell the receiver, guess which one, guess. You cannot tell that. A transmitter and the receiver needs to what? Needs to be in agreement. Clear? No response. Clear? Did the frequency change? No. Did the phase change? No. Tell me, what did you see here? Quickly. First of all, is it still a binary modem? Still a binary modem, 5 bit per second, 5 bauds. Question, what am I changing? Frequencies. How many frequencies do you see? 2 frequencies, one representing a 1, one representing a 0. Where is this coming from? Where is this coming from? That's the modulated carrier. That's the output of the modulator. Yes or no? Where is the input to the modulator? The input to the modulator is the bits. It's this one. 0, 1, 1, 0, 1. 1, 0, 1, 1, 0. That's the input to the modulator. The output of the modulator is this one. Clear? Okay. Tell me. What do I call this one? PFSK. PFSK stands for what? Binary frequency shift gain. Is the amplitude changing? Does the phase change? No. The phase also did not change. Yes? Now remember what I told you about analog modulation. In analog modulation, you cannot tell a what? An FM signal from a what? PM signal. Can you tell in the digital modulation? Very clearly. Let's see. Is it still binary modem? Still binary modem. Did the amplitude change? Did the frequency change? Did the phase change? Yes, it did. Now, I want you to see this. This is called differential. Going from 0 to a 1. Was there a phase change in the boundary? How much? 180 degree. Yes? Going from 1 to a 1. Was there a phase change at the boundary? No. So what does the receiver do? The receiver will track what? First of all, the receiver needs to synchronize with what? With the timing of each symbol. Clear? That's the symbol synchronization. And then he will what? He will see, is there a phase change or is there no what? No phase change. If there is no phase change, means what? There was no change in the bit. If there is a phase change, it means what? There is a phase change. Can you tell this from this? Oh, you can tell. If it's digital, you can tell it very easily that this one is what? FSK, whereas this one is what? PSK. PBSK stands for what? Binary phase shift gain. Clear? Okay. Binary modulation techniques are not in wide use anymore. Not anymore. I mean, not as it used to be before. Why? Because what is the K in binary modulation? K is equal to 1, which means what? It means, remember, what is the goal? From the user point of view, not from the telephone line or the transmission medium point of view. From the user point of view, what do you want? You want to increase the bit rate. The bit rate is what? RB equal to what? K, RS. How would you increase the bit rate? Look at it. You can either increase the K. K is what? It's the number of bits per what? Symbol, which I'll show in just a second. Or you increase what? R sub S. But keep in mind, R sub S cannot go over the what? Cannot go over the channel bandwidth. Are you following that? Otherwise, you are going to get what? You are going to get severe, what is known as what? Intersymbol interference. I'll show you that in detail later on. Clear so far? Cannot hear you. So what is other option is what? To increase K. Tell me, what am I doing here? Answer me. Well, first of all, what did I call this modulation scheme? QPSK. QPSK stands for what? Quadrature phase shift key. Quadrature phase shift key. Key. Explain it to me. One bit goes, remember, the transmitter or the device is generating bits in a serial fashion. Are you following? A serial fashion, one bit at a time. One bit goes into the modulator, nothing comes out. What happens to that bit? That bit is buffered inside the motor. So you can tell that once you have multi-level modulation, you are going to have what? Complexity in the modem design. Because you need what? You need buffering inside. Clear? Okay. Second bit goes in, one signal will be generated. How many signals do I need? First of all, what is the bit rate? 10. Yes? 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 0. What is the baud rate? 5. Are you following me? Why? Because K is equal to what? 2. Every what? Every 2 bits, you are generating what? One symbol. Which means what? Every symbol represents what? 2 bits of information. Clear? Clear? How many phases do I need? First of all, did I change the amplitude? No. Did I change the phase? No. Now, in reality, let me ask a question. This is very important, but we'll talk about it later. We are not ready yet. Listen to me. Is this a constant envelope modulation technique? I'm going to repeat it one more time. Is this a constant envelope modulation technique? No, it's not. Let's see what happens. At the boundary, what does the amplitude go from where to where? From positive to what? 0. Did you understand that or not? So at that point, by the way, have you studied constellation diagram? Yes. Signal constellation? Can you show it to me for the QPSK? How does it look like?
Circle.
One here, 4 phases. Cannot hear you. Question, are they on a circle? Why? Why are they on a circle? Because the amplitude is what? It's constant. But you would say, Professor, you just said the amplitude is not constant. Make up your mind. Going at the transition from one symbol, where are these? These are on a circle. Are they equally distanced from the origin? Why? Why? They all have the same what? They all have the same energy. Yes or no? Question. Why do I say that this is not a pure constant envelope? If this symbol, let's assume this one represents what? 0, 0. This one is 0, 1. This one is what? 1, 1. This one is what? 1, 0. This representation, by the way, later on we'll call it what? Gray coding, where one bit will be changing when you go from one symbol to an adjacent symbol. Don't worry about this right now. Don't worry about it. Just answer me the following question. Let's assume this is the symbol here. Yes? At this time, 0, 0. The next symbol, the next 2 symbols happens to be what? 1, 1. How are you moving? How are you transiting? From here to here. Are you going around a circle or you are going directly? You are going to go directly. I'm not sure you followed me here. Did you follow me or you lost me? You lost me. Did you lose me? Tell me the truth. I can handle the truth. You lost me here. Going from what? You look at the diagram. Look at the diagram. You can go from what? If you go, no, not this one. This one, I'm sorry. This one. When you went from, what was the phase here? Let's say 90, you went directly to what? To 0. You did not change the phase gradually. You changed it what? Instantaneously. So when you change it instantaneously, no, what am I? Here. Where did you go? What is the worst case scenario? The worst case scenario, if you go from this phase to this phase. Why? Because you are going to pass through who? The origin. And you will pass through the origin. It means the amplitude is equal to what? 0, which means the receiver will lose what? Will lose the coherency, will lose synchronization because he doesn't see anything. How do you go from 0 to 0, 0 to 0, 1? Can you show it to me? Here, in QPSK. This is how you go. On the circle or a straight line? Straight line. Answer me the following question. Is the amplitude changing a little bit? It's changing a little bit. Why? Because when you are here, what is the distance from this point to this? Is it the same as from here to here? No, it's not. It is only the same if you go around the what? Around the circle, not a straight line. Yes? But this is not as bad as this. Do you agree? Yes. Why? Because the amplitude is going to vary just a little bit. But when you go from here to here, you are going to pass it through who? Through the origin. Are you following me or not? And we need to be careful when we design our power amplifier, when we do have a what? A non-constant envelope. Now, in MSK or GMSK, to go from here to here, we will see when we get there, we will see that we are going to go around the what? Around the circle. Yes or no? Will it be slower or faster? If you go around the circle, it will be a little bit what? Slower. Are you following me on that? But on what the good thing that we get? If you go around the circle, the amplitude is what? It's constant. That's why we call it a constant envelope. Clear? Yes or no? Okay, good. Now, answer me the following question. How many phases do I need here? QPSK, that's why we call it a what? Quadrature phase shift key. Clear? Now, you might think about this as what? 2 PBSK in what? In perpendicular, in orthogonal. Are you following? In other words, you could also think about as what? As an I and Q. The I will take the what? The first bit. Yes? And the Q will take the what? The second bit. We'll talk about that in detail. This is just, I want to show it to you. Tell me, what am I doing here? First of all, what is the name of the modulation? QAM. QAM stands for what? Quadrature amplitude modulation. By the way, I forgot to mention that QPSK is widely used in second generation cellular, are you following me? And some satellite communications, but not in the what? Not in the new generations of what? Not in the new why? Because K is still what? High, or what is K? 2, which is it's a high number or a small number? I would like to make it a large number. However, what is the trade? Listen to me. How many phases do we have here when K is equal to 2? I have 4 phases. Yes? Make K equal to what? 4. Just an example. Just an example. How many phases would you get? 16. What are the phases? If it is 16, give it to me. What are they? 0, 22 and a half, 45, 67 something, 90. Are they getting closer and closer? The phases are getting closer and closer, which means what? It will be harder on the receiver to distinguish which one is which results in what? Increasing of the probability of error. Yeah, the receiver will begin making what? Making lots of errors. Clear? You have to remember one thing. These dots, these constellation points, is at where? At the transmitter side. When you reach the receiver side, those points are not going to be the same. They are going to be what? All over the place because of the noise. And I will show it to you in detail later on when we get to the modulation. Again, just an overview. Clear? Okay. Question, quickly. Where is it? Where is it? Question. First of all, look at the bit rate and look at the baud rate. Bit rate is 24. Baud rate is what? 8. Which means how many K? What is K? K is equal to 3. Which means how many bits per symbol? 3 bits per symbol. Clear? Answer me the following question. Look at it. Tell me what am I changing? I'm changing the amplitude and I'm changing the what? The phase. Question. How many amplitudes do you see? You see 2 amplitudes. How many phases should there be? How many symbols do I have? I have 8 symbols. So if I have 2 amplitudes, how many phases should I have? I have 4 phases. With 1 amplitude, I could have how many phases? 4 phases. With the other amplitude, I could have what? Another 4 phases. Yes? Can you show me the signal, the constellation? Just one example of a constellation. You can think about it as this way. Are you following me or you're losing me? You're following me or losing me? How many amplitudes? 2 amplitudes because they are 2 concentric circles. And how many phases? 4 phases. Notice, by the way, the phase of this guy is the same as the phase of this guy. Question, I mean a related question, but just to make sure you understand. The amplitude and the phase, are they dependent or independent? Independent. If I tell you what is the amplitude, can you tell me what is the phase? You cannot tell me what is the phase, and vice versa. And amplitude and phase are independent random variables. Clear? Okay. Quam, this is what RB equal to what? Equal to 3 RS. This is 3 is what? Is the K. Are you following me or not? Currently, the systems that are used in the 3rd generation or in the 4th generation, you go into what? 64 QAM, for example, 256 QAM. You can see that the constellation will become a little what? More involved, too many circles. Are you following me or not? Okay. By the way, constant envelope or non-constant envelope? This is very clearly, it's non-constant envelope. Are you following me or not? We will see later on that these are what? More bandwidth efficient than what? Constant envelope modulation, like the GMSK or the MSK. However, this one would require what? The power amplifier to operate in a what? Linear region. Are you following or not? If the power amplifier is a non-linear, and this one is a what? Variable amplifier, variable envelope, you are going to get all what? All the spectral side lobes that you have filtered it already. It will show up what? All again. It will tell you what? Hey, I came back. Hey. And with a smile, sarcastic smile. They tell you, you cut me off, I came back again.
Yeah, comparing this with the 8PSK, which one performs better?
This one will perform better than the 8PSK. This one. And this one is more efficient as far as what? As a power concern. This is a power efficient and what? Bandwidth efficient. But it's not as what? It's not as efficient, power efficient as the MSK stuff. But compared to the PSK, this performs a little bit better. By the way, you will simulate that. That is the topic of your first project, the MATLAB oriented. I will give you all types of modulation technique. I will tell you what, simulate the performance of each one of them in the vicinity of noise, in the vicinity of other non-linearities, and so on and so forth. Clear? And then you can deduce all of these based on the simulation result. You can tell what, you can tell the difference. Quickly, why do we modulate? Why do we modulate? I want you to understand one thing here. The size of the antenna, if it is going to be, when you talk about antennas, what is important stuff in the antenna? The size of the antenna, the efficiency of the antenna, the gain of the antenna. Are you following me or not? Did I mention the size? Yeah, and the directivity. Directivity means what? Whether it's unidirectional or it's isotropic. Question? Yeah, whether it's isotropic, maybe you will forget. Whether it's isotropic or what, or directional, and so on and so forth. Clear? As the frequency what? As the frequency goes up, which means what? The lambda goes what? Down, the size of the antenna becomes what? Smaller. So if you are not using modulation and you are transmitting a baseband signal with frequencies below 20 kilohertz, the size of your antenna will be what? In thousands of kilometers. Or you are going to carry an antenna thousands of kilometers on top of your head? You will become like the hunchback of Notre Dame. Are you following me or not? Clear? Okay. In addition to the size of the antenna, most important other reason for modulation is to allow for what? Simultaneous transmission. All of the basebands occupy what range? 0 to roughly what? 20K. If you are not using modulation, if you do not modulate the signal, all of them will be occupying the same band, 0 to 20K. So if you are transmitting them at the same time, do they overlap? Do they overlap? So how are you going to what? Separate them at the receiver? They all audio signals 0 to 20K. All of us are human. No one of here is extraterrestrial. Did you get my point or not? With modulation, modulation is the process of what? Shifting or up-converting the spectrum from what? An audio from a baseband to the what? To the RF. By assigning different RF signals, you are going to generate what? Channels that do not what? Overlap with each other. Clear? Allowing us to be transmitting them at the same what? Time, simultaneously. At the receiver, we can what? Select any channel we would like using our what? Our tunable receivers, tunable filters. Clear? Once we select the channel, we will always be able to what? Return it back through the demodulation process, return it back all the way to the what? To the basement. Do we need demodulation? If we don't use demodulation, we cannot hear it. Clear? So at the beginning, what do I need to do? Remember when I showed you the receiver last time? You need to select the what? The band first, and then you need to select the what? The channel. Once you select the channel, you need to get rid of the what? The carrier signal. You need to get rid of the carrier signal. Carrier signal did its job. Why do we call it a carrier? It's like a camel. Put the information on your back, reach there, and then give them the information. Goodbye, goodbye. I don't need you anymore. Did you get it or not? That's why it emerges. Now, some other important functions of modulation is that what? Sometimes interferences are what? More concentrated in a certain band than others. Are you following me or not? If you see, for example, cable, if you look at the spectrum of coaxial cable, you will see that it starts from roughly what? 5 megahertz. You might say, how come it does not start below that? Starting below that, there will be what? Interferences from what? Electrical or mechanical systems operating in the vicinity. Are you following that? Or some what? Or some amateur radios, ham radios operating in the vicinity. Some bands are more noisy than others. With modulation, what are you doing? You are leaving that band which is noisy, operate in a what? Larger band or higher band, yes? And then after you receive it, you can what? Return it to the original band. Clear? Okay. Again, and sometimes you need to place the signal in a frequency band where the requirements for filtering amplification are met with ease. This is what you were talking about a moment ago when you said if we operate at high frequencies, you are going to encounter a little bit what? More cost, more complexity in the design and stuff like that. Clear? We cannot use without modulation. To me, by the way, most important is the first two. Antenna, the antennas are getting what? Smaller and smaller. Can you see the antenna in your cell phone? You cannot even see the antenna in your cell phone. Clear? Clear? You are not going to carry the antenna on your back. Oh, what is this? It's ridiculous. And again, the simultaneous transmission of your signal. Choice of the modulation techniques. When you choose a modulation technique, what are the choices? Choices is the following. Is that first of all, you need to make sure that your modulation technique generate what is known as what? Compact power spectral density. Do you remember what power spectral density means? Yes or no? No, I don't think so. I need to refresh your memory, but I'm running a little bit out of time. You need to what? You need to make sure that your power spectral density is compact so that you minimize which effect? ACI, not the what? CCI. CCI is the what? Is the co-channel interference. It's within the same band. We are talking about what? The ACI. I don't want to see, when I show you shortly, I will show you for the QPSK. This is the QPSK. I will show you this later on. Look at this spectrum. I'm sketching, by the way, the absolute value of the spectrum. This is the power spectrum. And I am going to sketch the MSK or GMSK on top of it so that you can see this different. Follow me. Roughly. Tell me what you see. The main lobe is a little bit what? Wider, but the side lobes dies what? Faster. Why? Because these signals are what? Constant envelope. Did you understand what I just said or not? So even though the band, the main lobe is a little bit wider, but the side lobes dies what? Dies quicker. Clear? No response. Clear? Okay. So again, as I told you, you need to make sure that our modulation give me good bit performance measure, good bit error rate in the presence of CCI, ACI, thermal noise, and channel impairments, fading, multipass. The modulation technique needs to be providing you with what? With reasonable bit error rate. Now, the bit error rate requires, depend on the application. Some application, for example, voice application, you can tolerate what? Bit error rate 10 to the minus 3 or something like that. It's okay. For data, might not be okay. Clear, might not be okay. So it depends. Envelope properties, again, this is in the design of what? Our power amplifier. If the signal has a what? Relatively constant envelope, we can afford operating the power amplifier close to the what? Close to the knee. A reform which needs what? In the nonlinear region to achieve highest what? Efficiency. Power amplifier efficiency. Yes? But if the modulation technique is what? Non-constant envelope, it will result in what? It will result in generation of what? Of the spectral rigors, which means what? This one will what? Will what? Will contradict with this requirement. Did you lose me? Did you lose me? Oh, now the FCC, by the way, whenever they come with a standard, they will define what is known as what? As a spectrum, the emission spectrum, what? Boundary. Are you following the boundary? When they sketch the boundary, everything is in what? Like this. This is the spectrum. It tells you what? Tells you like this. It tells you your emission needs to be what? Bounded within the what? Within this. In other words, your spectral density needs to be like this. In other words, let me ask you a question. Is this satisfying the requirement of the FCC? Yes, it does. But if this one goes up on this, it's not what? It's not satisfying the requirement. So think about this as a what? As the ceiling that your emission cannot what? Cannot exceed this. And for different type of RF systems, different types of what? Of what is known as what? Emission? Anybody? Anybody? Somebody said something? Very good, very good, very good, excellent. Emission mask. And we will study emission masks later on when we study different standards. Clear? Okay. Operator, did I run out of time?
Yes, sir, we're out of time.
Okay, thank you.
This concludes EE 544 with Professor Zahid on Thursday, January 16th, 2014.